A newly discovered asteroid is passing close to Earth, and the timing is almost perfect for the internet. Its name is 2026 JH2, and it is not a planet killer. But its path is close enough to remind us how busy near-Earth space really is. From far away, the asteroid looks like a silent rock crossing a black ocean. Earth sits ahead of it, bright, blue, and completely unaware. The moon is farther out, but this asteroid comes inside that distance. That single fact is what makes the story feel so urgent. It will pass safely, but it will pass close. Close in space does not mean danger, but it does mean attention. Astronomers get a short window to measure it before it is gone. Every new frame helps refine its orbit. Every observation makes the next prediction more accurate. This is how planetary defense begins. Not with panic, but with tracking. The first part of the story happens in the dark, inside observatories. A telescope does not see a dramatic asteroid shape at first. It sees a tiny point that moves differently from the stars. That movement is the clue. One image alone is not enough. Astronomers need multiple images across time. They compare the object against the fixed star field behind it. The asteroid shifts, frame by frame. Software flags the motion and sends the object for follow-up. More telescopes begin looking at the same patch of sky. The orbit starts as a rough guess. Then the uncertainty begins to shrink. A new near-Earth object becomes a real track target. Inside a planetary defense control room, the question is simple. Where is it now, and where will it be at closest approach? The answer changes as new observations arrive. At first, the path has a wide uncertainty zone. Then the data tightens the corridor. Analysts are not guessing whether the asteroid is dangerous. They are calculating how close it will safely pass. The important word is safely. Close flybys can look terrifying online, but risk is decided by trajectory, size, speed, and uncertainty. When the orbit becomes clear, the alarm becomes science. The asteroid is not a threat. It is a chance to practice the system. To understand the distance, imagine the moon as the outer marker. Most people think of the moon as close, but space is huge. This asteroid passes much closer than the moon. That sounds dramatic, because it is rare enough to notice. But Earth is still a tiny target inside a vast orbit. The asteroid is moving through a corridor, not aiming at a bullseye. A close approach is like two cars crossing different lanes at different times. The numbers matter, but the geometry matters more. The orbital line bends around the sun, not around our headlines. Earth keeps moving too. The moon keeps moving too. The asteroid threads through the system and continues on. That moving geometry is the real story. The asteroid itself is probably dark, irregular, and difficult to see. It does not glow on its own. It reflects sunlight like a piece of charcoal in space. Its brightness changes as it tumbles. Those changes can reveal its rotation. A brighter flash may mean a flatter face turned toward Earth. A dimmer frame may mean the narrow side is facing us. That flicker becomes data. From that data, scientists can estimate shape and spin. Even a small asteroid carries a history. It may be a fragment from a larger collision. It may have crossed near Earth many times before. This pass is just the one we happen to catch. If the geometry is right, radar can turn a dot into a physical object. A giant dish sends a signal into space. Minutes later, a tiny echo can return. That echo carries distance information. It can also reveal speed with extreme precision. For planetary defense, radar is powerful because it sharpens the orbit. Optical telescopes show where the asteroid is on the sky. Radar can show how far away it is. Together, they reduce uncertainty fast. The asteroid does not need to be dangerous to be useful. Every close pass trains the network. Every measurement improves the next prediction. The quiet dish becomes part of Earth's early warning system. From orbit, the flyby looks different. The asteroid does not scrape the atmosphere. It does not pass between skyscrapers or satellites like a movie scene. It moves through a vast region above Earth. Satellites are tiny targets in that enormous volume. Still, the scale makes the pass feel uncomfortable. The asteroid is closer than many people expect space rocks to be. That is why these events catch attention. They make the solar system feel local. They remind us that Earth is not isolated. Small bodies cross our neighborhood all the time. Most are harmless. The important part is knowing which ones are not. Now imagine a different path, only as a simulation. If an asteroid enters the atmosphere, speed becomes energy. Air piles up in front of the rock. The surface heats rapidly. A glowing plasma trail appears behind it. Smaller objects break apart high above the ground. Larger objects can deliver serious regional damage. This is why size estimates matter. This is why early detection matters. This is why a safe flyby is still worth studying. The simulation is not a prediction for this asteroid. It is a reminder of why the tracking system exists. The best disaster is the one we understand before it happens. Planetary defense is not one dramatic button. It is a chain of boring steps that must work perfectly. Find the object, confirm the object, measure the orbit, estimate the size, share the data, update the prediction, decide whether action is needed. Most of the time, action is not needed, but the system still has to prove it can respond. A close flyby is a live rehearsal. The asteroid leaves, but the lessons stay. For the public, the flyby becomes a sky-watching moment. Most people will not see a dramatic fireball. With the right telescope, the asteroid may appear as a faint moving point. That is the beauty of it. The real event is subtle. A tiny dot crosses a field of stars. Behind that dot is a complete orbit around the sun. Behind that orbit is a story of discovery. The night sky becomes a live map. A backyard telescope connects to planetary defense. A small observation can join a global picture. The asteroid keeps moving. The observers keep tracking. The bigger story is what comes next. New survey telescopes will discover far more near-Earth objects. Some will be small. Some will be close. Some will become viral headlines. Most will be safe. But every discovery fills in the map. The future of planetary defense is not fear. It is a better inventory of our cosmic neighborhood. The more we find, the less surprised we become. That is the real power of modern astronomy. It turns unknown rocks into known trajectories, and known trajectories are manageable. At closest approach, the asteroid passes Earth and keeps going. There is no impact. There is no explosion. There is only a fast, silent flyby. For a few hours, the world had a visitor. Then the visitor moves back into deep space. The data remains behind, the orbit gets cleaner. The next prediction gets better, and the next asteroid will be easier to understand. That is why 2026 JH2 matters. Not because it is the end of the world, because it shows how we watch the world from space.